what I talk today about, want to talk today is not directly related to L functions. We know L functions in my talk, but it's about congruences among modular forms. So basically, it says something that Fourier coefficients of modular forms satisfy some relations among each other, yeah, and what one can do about this. And the background is a famous work of Searle, Formes modulaires et fonctions p-adiques, which appeared in the Antwerp volume. And after that, some people started to try to imitate this work, which was for SL2, for the Siegel modular case. I entered this subject by discussions with Nagaoka, and I find it very amusing that well, a lot of results are of similar nature for SPN, but the proofs which Searle gave usually do not transfer to SPN, and that's quite amusing. You need something new, which sometimes even makes the proofs for SL2 simpler, I think. Okay, so P will always be a prime. Most of the time it will be odd. And now I will go to congruent subgroups. So I will mainly use something like gamma 0 of P. What do I take? So gamma will... this is all A, B, C, D. Such that this C block is congruent to 0. This is our favorite group here, and our row usually I wrote GL of V, but now since we want to use Fourier coefficients as numbers and not as elements of an abstract vector space, I take coordinates. Yeah, so our V M, and so we fix coordinates here. So, to describe congruences properly, we do the following. Let's T. So I think the notion nu P has appeared several times. This is a nu P of P being equal to 1, and we introduce nu P of F to be the infimum this is and this infimum, thanks to the statement which I made last time, is not minus infinity, yeah? Because if F is not because of boundedness of denominators, yeah? We have a universal bound for the denominators, therefore this infimum is bigger than minus infinity. So, and now if we have f and g, mod p to the s will be defined in a strange way. I will explain why. Why do I do this in such a way? Why don't I say all the Fourier coefficients should be congruent mod p to the s? The reason is, if both modular forms are right away congruent to 0 mod p to the s, then there is no real congruence. Yeah, then both are congruent to 0 mod p to the s, but they don't share any property. Yeah, what you do here is well, morally what you do is, first you divide f and g by the highest power of p, by which all the Fourier coefficients are divisible, and after that the modular forms should be congruent mod p to the s. That is, and you can easily see that this is, you can change f here by to be g. This is symmetric. You can naively think that it's what you usually think, that all the Fourier coefficients are congruent to each other, but I want to, this is a very good formulation for this. Okay. So then the eigenvalues. But in general, congruence of eigenvalues does not imply anything about congruences for the Fourier coefficients. So as I explained previous lectures, the world of Fourier coefficients and the world of Hecke eigenvalues are different worlds in the context of Siegel modular forms. So we also have two worlds concerning congruences. And I talked today only about congruences for the Fourier coefficients, not about congruences for eigenvalues. Oh. Okay. Okay. For the scalar valued case, the following theorem. So if you have, say fj gamma, and f1 is congruent to f2 mod p to the s, then k1 is congruent to k2 for p is not equal to 2, for p is equal to 2 there's a similar statement, but I deliberately wrote down that it's the same as in degree 1 because we can ultimately reduce this statement to the degree 1 case. We can associate to f1 and f2 to elliptic modular forms which share the same congruence. Yeah, and then this is not really a new theorem. You can reduce the proof to the degree 1 case. Okay. And when I started to learn this theory, I found it very strange that it seems to be important to know the existence of modular form which is congruent to 1 mod p. Yeah? This looks strange, but it is an essential point. Since I want to keep these... okay. Yeah. Again, p should be odd. Now I write down 3 existence theorems. So there exists E p minus 1. Well, I do not always write determinant to. If there is just a number, I write p minus 1 instead of determinant to the p minus 1. P. This is for P is bigger than L. Such that this modular form okay. Yeah. I wrote down the first statement, which is weaker in some sense than this one, except for the fact that this is valid for all primes, mainly because I will give you a proof of this, and for the others are much more complicated in their proof and more delicate. What does this last theorem mean? It means this script f is congruent to 1 mod p for its expansion at infinity, but in all other cusps it is congruent to 0. Yeah, that is what it says. Yeah? This kp can be made explicit. Okay. And now the funny thing is I will tell you something about the proof of this first theorem. The other two are more subtle. How do you prove this in degree 1? Well, you just take the Eisenstein series of weight p minus 1, and the Bernoulli number for p minus 1 appears in the denominator of the Fourier expansion, and by Clausen von Staudt it has a p in the denominator, and then it's congruent to 1 mod p. Yeah, in degree 1 it's a consequence of Clausen von Staudt applied to the Fourier expansion of the usual Eisenstein series, even for level 1. But I wrote down in my previous lectures the Fourier expansion of the Siegel Eisenstein series, and there a product of several values of Riemann zeta functions appear. Yeah? And one of them is the one which also appears here, which would give congruence mod p. But in the numerator of the other Bernoulli numbers which appear, p may also appear. So the construction by Eisenstein series in higher degree to get a modular form congruent to 1 mod p works only for so-called regular primes in the sense of cyclotomic fields. It does not work for irregular primes because numerators in other Bernoulli numbers may compensate everything. So you have to do something else. How can you construct a modular form congruent to 1 mod p out of nothing? And this is one of the things which I enjoyed when I started together with Nagaoka to look at these things. So Bernoulli numbers may be a source of such congruences. But let's look at theta series attached to integral quadratic forms. Such integral quadratic forms sometimes have automorphisms. And suppose you have such an integral quadratic form which has an automorphism of order p. And suppose that this automorphism has no fixed points in z to the m unlike different from 0. Then the representation numbers, which are the Fourier coefficients of the theta series, they all must be congruent to 0 mod p because you act on them without fixed points by some automorphism of order p. So of EP minus 1. So let's look at something which is called AP minus 1. This comes from the theory of root systems. So on this we can act by SP. Order P, tau of order P, so we can act here by acting on the coordinates, and if it takes, say, something which just moves the coordinates by 1 to the neighboring coordinate, this thing acts on AP minus 1 without fixed points different from 0. And quadratic form S how do we, well, this is a lattice in Z to the P, and we equip it with the usual Euclidean norm, and then this corresponds by choosing what is called a Gram matrix. We get the even integral quadratic form here. Let's take this with some of these, and then theta n of S, this theta series, will be congruent to 1 mod P. Because all these Fourier coefficients that I called last time AST R, comma N, so this is a new source of congruences for modular forms, that you use theta series with automorphisms of order p and having no fixed points. So, okay. Sorry, I have to erase this because I need this existence theorem over there. Maybe keep it for a moment. But as I said, this is something typical for extending things from degree 1 to degree n. You need something new very frequently. So now, what is the definition of p-adic mesures? So we fix rho, and we look at a formal Fourier expansion A of t trace of tz just a formal series. So we may change the determinant part of the weight for, now this is important. We take now level 1. Yeah. So, in other words, if you go to a fixed Fourier coefficient and one component of it, then these components of the fj converge p-adically to the corresponding component of a of t. But all of this happens uniformly in the Fourier coefficients. Yeah, that's important. It's not that for each Fourier coefficient you have such a p-adic convergence, but you have it uniformly. Yes, and I might request here that the Fourier expansion here is not in Z, but in Zp, which means we allow other denominators, but not at p. Yeah, it's not Z. It's not p-adic numbers. It's p-adic numbers intersected with q. Yeah. So now what can we do with such a definition?
Sorry, can you maybe explain what you mean by where does fj live? I mean, in the space of modular forms or with respect to rho, and then you have set p, so what does it mean?
So say it again.
The parentheses here.
Yeah, the formal power series. Well, of course I wrote, you can use this as formal variables.
Yeah.
Yeah? And then you have just a formal power series giving these a of t. I could as well give you a sequence of a of t. Yeah? And these a of t arise at p-adic limits of t Fourier coefficients of modular forms of level 1.
Okay, but this is not the same thing as requiring that we have SP and set P instead, that we have coefficients that the matrices are.
I don't understand your question. Sorry.
Just remind us what you mean when you add on the ZP to the definition of the sequence. So the Fij are in this space of modular forms.
Yes.
With some additional restriction on the coefficients.
Here it's.
Yeah.
Here I put a restriction on the coefficients. I want the modular forms to have integral Fourier coefficients in P. I mean,
p-adic or
yeah, no, not p-adic. It's not p-adic. This. So. No. The P. So there may be numerators in the Fourier coefficients like outside of P. Yeah. So the modular forms have rational Fourier coefficients integral at P. Yeah. Actually, I would not really have to request it. Ultimately, due to this, in the sequence, they would have p-adic integral Fourier coefficients. Okay, now the only examples which you know a priori are the Siegel modular forms of level 1, which have integral Fourier coefficients. But what else? And this is one of the points which you can make about p-adic modular forms. A lot of things which are not modular forms for SP and Z are nevertheless p-adic modular forms. And I emphasize that we request them to be limits of sequences of level 1. Yeah. So therefore the following very bad, because I need the notations over there. I want to keep that. And the point is that here I have gamma 0 p to the n, and here I have SP and Z. Yeah? So this is a real statement. Yeah? So in other words, maybe again SCP. I should say all this works instead of over the integers, it works in an arbitrary algebraic number field. Yeah, when you choose some valuation there, it is not restricted to this. Okay, but it should be clear this is a real statement, yeah, because it connects modular forms for level to modular forms of level 1. Yeah? This is something like lowering of levels. In particular, it says that a modular form for gamma 0 p to the n is congruent modulo any power of p to some modular form of level 1. And the proofs are different actually for capital N being bigger than 1 or n is equal to 1. So let me shortly write something about the proof for n is equal to 1. So and now that's the reason why I wanted to keep this. I take this. I take this product here, and here I take some power of this function. Now this is not what I want, because I want something of level 1. But now we already know what we do, how to get level 1. We apply force, yeah? We average. So we take SP. If we look at two different kinds of contributions, one is the trivial one, and what's happening there is just f times the p to the t power of this. Now, if something is, this one is congruent to 1 mod p, but if you take a p to the t power of it, it becomes congruent to 1 modulo p to the t plus 1. Yeah? So, is congruent to f Now what's happening there? The new p of this, well, this we do not really know what it is, but it's something, some finite thing, plus p to the t, because all of this was congruent to 0 mod p. So it means this function here, when you look at its Fourier expansion in the other cusp, it's congruent to 0 modulo a sufficiently high power. Yeah. And so by enlarging t, we see that we can make f to be congruent to this function of level 1 modulo an arbitrarily given power of p. So in other words, f is congruent to a level 1 form. And so it means that these kind of things converge to f t goes to. So, but this is the same proof as you can find it in Searle up to the construction of this function f kp. Yeah, that's the same. So if n is bigger than 1, one has to use UP operators. You have to keep in mind UP operator, when you apply it to a function for on gamma 0 p square, then the result will be on gamma 0 p. Yeah? That is something that you learn about Hacker operators. Use UP to decrease n. Now this is not so easy, in particular in the vector valued case, but this is the basic idea, what you can do. And again, in particular for the vector valued case, here you need some new idea. Okay. So the story is that you can change levels and so modular forms for gamma 0 p to the n are examples for p-adic modular forms. Okay, and the other thing fits, the other example which I want to give you fits very well to the my last talk. I emphasized last time that derivatives of modular forms are not modular forms. But for the p-adic theory, it doesn't matter. Modular forms, derivatives of modular forms will be modular forms again. So this is the second topic, and then I will finish. So, let me start ordinary modular forms. So you have I and Z, and then typical thing what we do, this is not stupid notation, but it was introduced by Ramanujan, and how should we criticize Ramanujan? Yeah? We cannot criticize him. How can we prove that this is and that I write down the thing for SL2Z is justified because the proof I give is not the proof which you usually find in works on SL2Z. It's a proof which works for SPN. Even for SL2 it's a new proof, and I take the Rankine brackets of my F so remember, this was a modular form for gamma 0 p congruent to 1 mod p. Yeah, let's see. F p minus 1 minus k. So this is weight k. Now I have slightly renormalized things, and now I divide here by the weight of this f times f p minus 1 prime. So now I prefer, because of this stupid thing with the 2 pi I, instead of using the derivative, I prefer to use the theta here. Then everything is rational. Yeah, this has just been a renormalization by. And now you see this is congruent to 1 mod p. And what is about theta here? This is congruent to 0 mod p, and so everything is congruent to theta of f mod p. Now, to get congruences, yeah, there is one problem. This was such as yeah, because this fp minus 1 was a modular form for gamma 0 p. But that's not so bad by the theorem over there, once it's congruent to modular form for gamma 0 p. So, okay. Now some problem arises. What about the higher powers? If instead of fp minus 1 you take something that is congruent to 1 mod p square, its weight has to be congruent to 0 mod p times p minus 1. Yeah? For example, you can take just the piece power here. But the problem is that so here this appears in the f times theta. How's this? The Rankine-Cohen bracket is made in such a way that here this weight appears in the denominator, and you get here this thing in the denominator, and doesn't help you that theta of f is congruent to 0 mod p to the m, because you have this denominator here. Yeah? So this does not work. Does not give congruence Still, the story is not so bad. And then this problem of p to the m minus 1 here in the denominator will be compensated by taking the derivative. Yeah? If you now take the derivative of this function, the p to the m times z will give you an extra p to the m outside. Yeah? Will kill maybe even this is enough. And then from this you can go down to SL2Z. I explained this for the Rankin brackets in detail because word by word this works in the Siegel case as well. But now scalar values. Now you have to recall from my first talk that T to the J, this is a matrix a symmetric matrix of size n over j, consisting of the j minors of T. Yeah. This is in, yeah, wherever, say, n over j plus n over j symmetric. Yeah. So to give you an example, theta n over f is just determinant a of t and theta 1 times t and theta 0 is just f itself. Yeah? So and how can we show that these things are p-adic Siegel modular forms, now vector valued, unless j is equal to n. Now again we have to use Rankin brackets. So the theorem is okay, well, it may be gamma 0 p to the n. That doesn't really matter because we can switch this to level 1. So theta j is p-adic. And the proof goes in a similar way as before, and I will not give the details. And the main point is that there exists a corresponding Rankine-Cohen bracket. Namely, yeah, I may call it K, L, rho J. Rho J is the appropriate representation of weight 222, comma 0, 0, 0, which acts on such things naturally and which are introduced. This is highest weight. J. So it goes from holomorphic functions holomorphic function Hn C N and here we have the slash action. By K, here we may have any f and g. It starts with theta j f times g plus a lot of things which all will involve derivatives of g. G itself only appears in this first term. Now, and if we apply this kind of thing, now I cannot tell you now how one gets this. One can directly write down explicit formula for the complete Rankine-Cohen bracket here. But this involves a lot of multilinear algebra, but we do not really need those other terms. It's this term which is interesting, and the theorem we get in the same way as before. To your f. And I call it, get lost in my notation. This was script. Oh no, I don't know. I just need fp minus 1 p to the m minus 1. And then you get that the theta j of f is congruent to a modular form first for gamma 0 p to the m or m minus 1, doesn't matter so much. And then you can do the level change mod p to the m to 1. In other words, the theta j f is a p-adic limit first for gamma 0 of some power, but ultimately for SPNZ. Now, this does not only work with these specific theta operators, it works with any Rankine operator which has the initial term of the form applying a differential operator to the first one times the function from the second argument. Yeah? If it's just of this form, then you can do everything in this way. Now, these were examples that derivatives of modular forms will be p-adic, and also modular forms for gamma 0 groups will be p-adic modular forms. Yeah?
Special values of the functions are congruent to express properly.
Well, I think I'll stop here. This was also a good motivation to consider these Rankine-Cohen brackets which I introduced last time. So these theta operators destroy the modularity, but not quite, because after all, when we just look at congruences, we still have something which looks like a modular form. And I think this proof by using Rankine-Cohen bracket is the most natural one. But it was not invented at that time. When they did, when Serre introduced this, he worked with E2, with the Eisenstein series of weight, non-holomorphic Eisenstein series of weight 2, and things like that. But with these Rankine brackets, we can do it very naturally. So now some question, of course, remains: what have p-adic modular forms to do with L functions? This I don't know, and maybe you can answer this.
But general ideology that special values of the functions are congruent to expressed for coefficients. So whenever you have...
Yeah, but the p-adic interpolation of the L values have nothing to do with p-adic modular forms.
Even in Serre's example, you have, how to say, series of congruences between the Fourier coefficients which produce you.
Yeah, this is p-adic. Yeah.
So in this sense, it is.
Yeah, but this kind of proof of Klingen's theorem p-adically by Serre, it has never been. There is, I don't know any analog in higher degree.
Yeah, so it would be good to develop it. What about Hermitian case, by the way? What difficulty do you see to extend it to the Hermitian?
I don't think there is any particular difficulty to extend the techniques which are used will all be there.
It's always exists, congruent to one modulation.
Yes. We can certainly do this in the same way by using Hermitian modular forms, Hermitian theta series. So that will work.
Yeah.
Someone has to write it. So thank you for this extra hour. Was it 1 hour? I don't know. I did not look at my... Okay, 1 hour. This was accidentally. I did not control it. Okay, thank you.